This second video in how to read skeletal line structures and chemistry will dive into some more examples. Back to this ring again, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is also C9, and to determine the number of hydrogens, we're going to do the same thing we did in the last video, which is counting up where they would be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's take a look at that double bond at the end, because sometimes people get those mixed up, especially when there is a double bond at the very end of a section. There are 2 bonds already connecting to this terminal carbon here, which means that it can have a maximum of 2 more bonds, and those would be hydrogens. The carbon that is adjacent to it would have only 1 spot available. So counting up all of our pink notches, which represent hydrogens in our analyzing shorthand, there would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is the entire formula because there is no other atom explicitly shown. Let's take a look at the second example. There's a chlorine on the end, so we're going to leave that alone for now and go around our 5-carbon ring. 1, 2, 3, 4, 5. So it's C5. And now we count where our hydrogens could possibly go. Only 1 spot available here, 1 spot available here, 1 spot available here. There are 2 here and 2 here, and that is all. Counting up our little notches, we have 1, 2, 3, 4, 5, 6, 7. So the formula would be C5, H7, Cl. An alkane is a substance that has no double or triple bonds and has only carbons and hydrogens. An alkene has a double bond, and an alkyne has a triple bond. This third example here would be an example of an alkyne because it has a triple bond. And that is going to count as kind of like a vertex still, or the end of a line. It falls somewhere in a gray area between, but the counting is the same. Let's find all of our carbons. 1, 2, 3, 4, 5, 6, 7. So the formula for this would be C7, counting where our hydrogens could go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that would be the complete formula, C7, H12. If I'm going to circle this triple bond here, neither of the carbons in a triple bond that is in the middle of other carbons in a chain can have hydrogens on it, because both of those carbons has 1 and then 3 bonds, so for a total of 4 bonds. So they are all full up, and the formula would be C7H12 and nothing else. I've decided to not make a third video and just add it on to what I was just doing because it was only a few minutes long. So let's do 2 more complex examples. Counting up all of our carbons, we have 1, put the green color, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have C14. Finding where our hydrogens would go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it would be H19. And then you're going to tack on all of the non-carbon, non-hydrogen elements. We have an N, and then we have 2 oxygens. And that is all. As you can see, these are not that bad, and in a slightly nerdy way, they can be a little fun as well. In the very last example, we're going to count up all of our carbons again, and we have something that looks a little different, those weird looking bonds I'll explain in just a minute. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So we have C, 21. Finding our hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the H26. The final component of this compound would be chlorine, and then nitrogen and oxygen. And that would be it. We cannot leave without first addressing what these weird looking bonds are that some people may have seen in Gen Chem or in organic chemistry, and you may not have seen before. But these bonds here, these wedge bonds and these dash bonds, those are simply single bonds. But the reason that they're not regular looking lines is because molecules exist in three-dimensional space, and therefore they can have some orientation, some stereochemistry, that indicates that the three-dimensional configuration of the molecule has some parts that are going out of the screen or the page at you, so to speak, and behind the screen or the page. This is not a lesson on stereochemistry or three-dimensional Vesper theory or anything like that. All you've got to understand is that when you see a wedge bond or a dash bond, it's simply a single bond that is giving the viewer a little bit more information about the three-dimensional orientation of the molecule, but it's nothing more than a single bond that has a certain direction that it has or is taking another part of the molecule with it. As an example, I'm going to draw methane. Methane, in general, looks like carbon with 4 hydrogens on it. That would be a structure that doesn't give you any information about the three-dimensionalness, so to speak, of it. However, if you've learned anything about Vesper theory, you know that methane is a tetrahedral molecule. So here's methane drawn again to show you what it looks like in a more three-dimensional way. You have a hydrogen that's coming out at you a little, and you have a hydrogen that's going or receding to the page. So if you want to think about this as a floor, the hydrogens here, here, and here are kind of like the tripod legs. They are touching the floor. If you were to build a three-dimensional molecule of methane, you would have 3 hydrogens touching whatever you're sitting the molecule on. The carbon that is floating above the base, it is not on the floor, and you have a hydrogen that is kind of at the peak. So that just gives you an idea of what those wedge and dash bonds really mean. That is all there is for this video on reading line structures, and hope you enjoyed.